In the materials for week one, in the introduction, I included a chapter on variance and the relationship between variance, ICC, standard deviations, and spans. And then in the assignment for week one, I included a similar table, which you see over here. This is the data set that I was working with in the example that I used in the assignment for week one. We assume that students are nested within classes, which are nested within schools, which are nested within districts. And I wanted to use this example to basically review in this video the same material that I had over here to make sure that, I guess, to provide you another opportunity to look at it and maybe to elaborate on it a little bit. The first thing that we have to understand is that what we're dealing with over here is how the scores or means vary in the population. We're not talking here about the sample or sampling error. Rather, we're talking about the actual dispersion of scores in the population. So these are population parameters. We're using the example of SAT, and we're saying that the standard deviation of SAT scores across students is 100 points, which is in fact the standard deviation of that test. But that refers to students across classes, across schools, across districts. Let's assume that's the standard deviation for all students in the state is 100 points. If the standard deviation is 100 points, then the variance, which we see over here, this is the column for variance, this is the line for total, is 10,000, which is simply 100 squared. Now, a basic point that applies to analysis of variance that all of us are familiar with from basic statistics is that variance can be partitioned into its component parts. But that variance can be partitioned as follows. 8,100 points out of that variance is going to be the variance of student scores about the mean within a class. So in other words, if we go to a particular district, and then in that district we choose a school, and in that school we choose a class, within that class we look at the students, the variance of the student scores inside of that class is going to be 8,100. Similarly, if we go to a particular district, and then within that district we choose a school, and then we look at the variance of the class means within that school, the variance of those class means is going to be 1,200. And by the same token, if we choose a district, and then within that district we look at the school means, the variance of those school means is going to be 500. And finally, if we go to the state, which is our entire population, and we look at the variance of the district means within that state, that variance is 200. So if we're trying to understand where a particular score comes from, or I guess more to the point, if we're trying to understand the deviation between any student chosen at random in the state and why that score deviates from the overall mean of 500, some of that can be attributed to the district that the student is located in. Some of that can be attributed to the school that that student is located in within the district. Some of that can be attributed to the class that school is located in, that student is located in within the school. And then some of that is just variation from student to student within the class. And we also can get a sense of how important each of these is. In other words, the majority of the variation seems to be taking place at just across students within classes. The second most important source of variation is class to class within a school. The next most less important part is school to school within a district. And finally, there is some impact of the difference from district to district, but that's a smaller portion of this. When we're computing power, we can actually work with these numbers. But the problem is that the variance is going, first of all, it's not an intuitive value. And second of all, it is going to depend on the particular scale that we happen to be using. So these variances make sense if we happen to be using the SAT, but the variances are going to be completely different if we happen to be working with something like a GPA for the sake of argument. So by the same logic, if you know, and generally when we work with power analysis, rather than working with the raw mean difference, we work with a standardized mean difference so that everything goes back onto the same scale. And we know, for example, that a d-value of 0.5 might be considered medium in social sciences, and 0.2 is small, and 0.8 is large, and so on. By the same logic, we can use a standardized scale when talking about the variances, and that's exactly what we do over here. And the way that we standardize this is, instead of simply taking each of these numbers as a raw value, 200, 500, and so on, we divide that number by the total variance to get a proportion. So that if the total variance in this case is 10,000 and the variance of districts is 200, well, 200 over 10,000 is 2%. So 2% of the variance is attributed to districts, 5%, which is 500 over 10,000, is attributed to schools, 12% is attributed to classes, and 81% is attributed to students. Excuse me. In this case, the translation is fairly obvious because we happen to have a round number over here, but moving from raw variances to ICCs is not going to be that obvious if this number didn't happen to be a round number. And so this is immediately helpful, and it allows us to actually publish tables of expected values of the ICC for different populations and so on. You'll notice over here, by the way, that once we've moved to a standardized scale, the total variance is going to be 1, and therefore these are not only the proportion of the total variance, but they actually are the variance that we would get if we were, for each of these levels, if we were working with a standardized scale. Since in fact we are working with a standardized scale, this would actually be the variance in standardized units for districts, schools, classes, students, and so on. The reason that this is important, the reason that we need to know the variance or the proportion of variance, is that we're going to be figuring out how much sampling error there is at each level. That sampling error is going to depend on the population variance at that level and the number of units at that level. So it really doesn't matter. We're going to be using one of these numbers in the computations. The nice thing about working with the ICC is that it's independent of scale, so that if we have the ICCs, we can go ahead and do the power analysis even if we don't know what the original scale metric was. The problem, that's the nice thing about working with the ICC, the problem with working with the ICC is that you might go to a table where they say, well, the ICC for districts in something like this is 0.02, and you can take it on faith, but you don't necessarily have a really good feeling for what that means. You know that you're working with SATs. You know that you expect the SATs mean to vary from district to district across a certain range of scores. But how do you know whether or not the ICC of 0.02 corresponds to the range of scores that you're thinking about? So while these two columns over here, the variance or the ICC, are the numbers that we actually use to compute power, the problem with them is that they're not intuitive. If we want to take these numbers and translate them into a metric that we understand so that we can say whether or not these values are plausible, generally the way that we would do that is to put them back onto a raw scale. And that's fairly simple. If, for example, if the variance for district means is 200, the standard deviation for district means is simply going to be the square root of 200. It's going to be 14.14. Well, if the standard deviation is 14.14 and the mean is 500, then we know that if we're going to assume a normal distribution, which is an assumption that we make, that approximately 95% of all districts are going to fall within a range that goes from 2 standard deviations below the mean to 2 standard deviations above the mean. That range, or that span of scores, therefore, is going to be 4 standard deviations, 2 below and 2 above. So to get the span, we simply can take 500. To get the span, we can simply take 14.14, which is the standard deviation, multiply it by 4, and we're going to say that we expect that about approximately 95% of all districts are going to fall within a span of scores. Within the scores are going to span about 56.57 points. And to put that in context, we can simply take this and center it on the mean. So if the mean is 500 and there's a span of 56, we can take half of that and put it below the mean, which gives us 471 as the lower limit, and half of it and put it above the mean, which gives us 528, which is the upper limit. The way that we get these numbers, again, to be explicit, 500 minus 2 standard deviations gives us this. 500 plus 2 standard deviations gives us this. And then we can do the same thing for schools, and we say that we expect that if we have a school where the mean is 500, that the lowest if we have a district where the mean is 500, then the lowest school in that district is probably going to have a mean of about 455, and the best school in that district is probably going to have a mean of 544. Let me be clear about this, because this is not necessarily intuitive. The span is a number that we can use without qualifying it. Once we're assuming that the standard deviation for districts is 14.14, we're saying that the span from the lowest district to the highest one is going to be 56.57 points. Once we say that the standard deviation for schools is 22.36, we're saying that that span from the lowest school to the highest school within any district is going to be 89.44 points. So those spans are without qualification. The range, however, does need to be qualified. When we're talking about districts, once we've said that the overall mean is 500, then if we know the span is 56.57, then the range must be 471 to 528, because that's the only way that we can have an overall mean of 500 and have this span. But once we come to schools, well, we're saying within a district, the school means are going to span about 90 points. So if we happen to be talking about a district where the mean is 500, then the school means are going to range from 455 to 544. But what happens if we happen to pick a district where the mean is not 500, but where the mean is 490? Then the school means are not going to range from 455 to 544. Rather, they're going to range from 445 to 534. So when we give the range, we're always saying on the assumption, or rather in the example, where the district happens to have a mean of 500, this is the range that we're talking about. Similarly, when we move down to classes, the range, if we happen to be talking about a school that has a mean of 500, then the class means are going to range from 430 to 569. But if we happen to pick a school where the mean is not 500, where the mean maybe is 450, then the range is going to be shifted 50 points to the left. It's going to be 380 to 519. And similarly, when we get down to students, if we happen to be talking about a class where the mean is 500, the student scores might range from 320 to 680. But if we happen to pick a class where the mean is 400 instead of 500, then the student scores are going to range from around 220 to around 580. So the range, except for the top level, the range is always given as an example. The span, however, is always assumed to be the same. It is because we haven't centered it around any number. Now, there's one additional thing that we should take a look at. Okay, I've duplicated these numbers over here in the program. I've put in an ICC of 0.02, which matches this, 0.05 for the second level, 0.12 for the third level, and internally the program is computing 0.81 as the analog to the ICC for students. We can see over here the span is 56.57, 56.57, 89.44, 89.44. The range is 471.72 to 528.28, 471.72 to 528.28. So all the numbers match. Let me come over here and generate a report. And we come over here, and I'm going to go down to the page that deals with the dispersion. Okay, so we're looking over here at okay, this is the variation in means. Excuse me, what we have over here is the variation in means within levels. So this is the variation of means across districts. This is the variation of means for students, for schools within a district. And this is the number that we saw before. This is the variation of means for classes within a school. This is the number that we saw before. And this is the variation of student scores within a class. This is the number that we saw before. But there's another way of looking at this. If we're looking at districts, then that's going to be the same. Basically, we're looking at all the districts within a state. So that ICC is 0.02. The variance is 200, whether we're looking at districts within the state or looking at districts within the state. Those two are the same. But when we come to the next level, when we're looking at the variation of means across schools, there are two ways that we can look at this. We can talk about the variation of means across schools within a single district, or we can talk about the variation of means across schools across districts. And obviously, I made the point a minute ago that if we're saying that the schools are going to span 89 points within a single district, where that district happens to have a mean of 500, obviously schools are going to span a wider range if we're looking at schools across districts. Because if we happen to pick a school that has a mean of 500, we know that the school means are going to range from 455 to 544. But if we happen to pick a school a district that has a mean of 470, then all of the school means are going to be shifted downward by 30 points. And if we happen to pick a district that has a mean of 528, then all of the school means are going to be shifted upward by 30 points. So the span of school means across districts is going to be wider than the span of school means within a district. Similarly, if we look at classes, we said that the span of class means within a school was going to be about 90 points. But if we're looking at the span of class means across schools and across districts, so what we've done over here in the report is we give the span of means, not on the left we give it within the next higher level, and on the right we give it across all the higher levels. What's the purpose of this? Well, again, the purpose is to make sure that these numbers are plausible. Perhaps, if we have a sense that the school means are going to vary across a span of about 90 points within districts, then we can take a look at this number and make sure that this matches our expectation. But maybe the researcher does not have a lot of experience in how much school means vary within a district, but does have a pretty good sense of how school means vary across the entire state. In this case, they can go in and take a look at this number and make sure that this is consistent with their expectations. So this is simply another way of looking at the same data.